So in today's video and for most of the rest of the unit, we will be taking pretty much everything we know about functions, collecting that data and using it to be able to sketch what the graph looks like. Now as I go through each of the different types, I'll be going through them pretty quickly. If you'd like to pause it and write them down, you can as I am doing that. Now calculus enables us to find the important things in the graph. We've seen how we can find like maximums, minimums, inflection points, things like that. And you might ask, well, why don't we just use the calculator? Why do we need calculus to do that? Well, let's take a look at this graph. It looks roughly like an x cubed graph or so, where it like flattens out and then goes back up. It appears that it doesn't have any maximums or minimums. But if we examine a little closer and zoom in, we do see that there is, in fact, a little bit of a decrease there in the function. So we do get a maximum and a minimum. So if you're just looking at the calculator and eyeballing it, you might not find that. Calculus, though, would find that for us. When we take that first derivative, we would see there are some values that would make the derivative 0, and we could then find those maximums and minimums. So there's about 10 criteria or so, like 9 or 10, that we will look at when we are graphing a function. First thing we'll always look at is what is the domain of the function. If it's a polynomial, we'll have all real numbers. Are there any places, if it's a rational function, where it will be undefined? So the domain is the first thing we'll start out with. Next, we'll want to look at the intercepts. Well, every y-intercept, so a point like this, every y-intercept always has an x value of 0. So you're going to find f of 0. You're basically going to plug in 0 for x to find when it's going to intersect the y-axis. So you'll always get some point 0 comma something. Now because it's going to be a function, you can only ever have one possible y-intercept. To find the x-intercepts, every x-intercept has a y value of 0. So you'll put 0 in place of the y. So you'll have something comma 0 for those points. Now, if you have some case where, like, say it's a polynomial of like degree 4 or higher, it's okay if you don't find the x-intercepts there, because that might be something you can't do without your calculator. But anything that's cubic and less, you should be able to find the roots for the function. Now, your x-intercepts, you can have more than one. Y-intercepts, because it's a function, if it had more than one y-intercept, it wouldn't pass the vertical line test. But x-intercepts, you could possibly have multiple. Next, we'll look at symmetry. Now, symmetry is not... It can be done without finding the symmetry, but symmetry can make your life a lot easier and make the process less. First off, even symmetry. A function with even symmetry, when you see the graph, is symmetric about the y-axis. The reason this could help us is if you realize it has even symmetry, you only need to know one side of it, and then it's just going to reflect over the y-axis. Okay, so that's why our work would be cut in half. So an example of something with even symmetry would be an x squared graph. Now, how do you find if something has even symmetry? You replace all the x's with a negative x, and if it comes back to be the same thing, then it's even symmetry. So let's look at it with the x squared. Our original function is y equals x squared. If we replace our x with a negative x, so that means we now have negative x being squared. Well, negative x squared is just a positive. So notice we get back the same thing as the original. So anytime when you put in negative x for all the x values, if it just simplifies back to the original, then that means you're working with an even function. Here's another example of an even function, symmetrical at the y-axis. And a few examples of functions that are even. X squared we just saw, x to the fourth. Absolute value is even, because when you put in the negative x, absolute value of a negative x is just a positive x. And cosine is also symmetrical at the y-axis, so it is considered an even function. Now, odd functions are when you sub in a negative x, it's the same as if you had just negated the entire original function. Now, if there's multiple terms, that means you would have distributed it through. So, for example, if we have y equals x cubed, when we sub in a negative x cubed will come back as negative. So that's the same as saying y equals minus and then x cubed. How those two things are different, the negative x in parentheses raised to the third, it has the negative raised to the power, whereas the last thing there, just the x is raised to the power, but the whole function is negated. When you have an odd function, it is symmetric about the origin. Something is symmetric about the origin if when you turn your paper 180 degrees, it looks exactly the same. So let's look at this one here. Okay, this function here, when we spin it 180 degrees, it looks exactly the same as the original. So therefore, that's an example of an odd function. Some other examples of odd functions, you have x cubed, x to the fifth, sine x, and so forth. If you're working with just a polynomial function, if all the exponents are even, then you're dealing with an even function. Now, a constant is considered an even function because it's really like having x to the 0. So if you had like y equals x to the fourth plus 2x squared plus 7, that's even, because when you put in a negative x, it'll come back positive. And the 7 is like saying x to the 0, because x to the 0 is just 1. Now, an odd would maybe be like x to the fifth minus 7x cubed plus 6x. All the exponents are odd. Now, the next thing is if a function is periodic. Examples of periodic functions are like sine and cosine functions. Because they repeat over and over again, you only have to find one period of them and then just duplicate that cycle every time. Here's an example of something that's periodic. You've got the same section that is just repeated over and over again. Now, in reality, we're not going to see too many that are periodic. Next is our horizontal asymptotes. In general, we know that a horizontal asymptote is what is happening to your function when your x's either get really, really big or really, really small. So either going towards positive infinity or negative infinity. The most common place we see horizontal asymptotes is with rational functions. There's four cases we'll see for horizontal asymptotes. Let's say we had y equals 2x plus 7 over x minus 3 as one case. Let's say we had y equals 2x squared plus 7 over x minus 3. Let's say we had y equals 2x cubed plus 7 over x minus 3. And then let's say we had y equals 7 over x minus 3. These are the three different types of scenarios we could have, and you should have seen this in pre-calc. The first is when the degree is the same. These are both raised to the first power. When that's the case, you take the ratio of the leading coefficients. So in this case, it would just be 2 over 1, so y equals 2 would be our horizontal asymptote. The next case is when the degree of the numerator is 1 bigger than the degree of the denominator. We have an x squared on top and x on bottom. In that case, you will get a slant asymptote. And we will look at those in more in depth later on. You probably saw one or two of them last year. We'll see a little bit more how to do them later on, but it involves synthetic division. When you get the slant asymptote, it'll basically be an equation of a line, like y equals x plus 2 or something. The third case is when the degree of the numerator is more than 1 higher than the degree of the denominator. In that case, there is no horizontal asymptotes. And then the fourth case is when the degree of the denominator is bigger than the degree of the numerator. So the degree of our numerator is 0, our denominator is 1. That case will always be y equals 0. So I could also, maybe if I made this 7x and I made this x squared, it would still be y equals 0 because the degree of the denominator is greater than the degree of the numerator. Next, vertical asymptotes. Vertical asymptotes are where the function would be undefined. Now, two things to look out for. In general, with rational functions, it is where the denominator is equal to 0. So in this first one here, the denominator would be equal to 0 when x is equal to 3. Now, one case where you could have the denominator equal to 0 but not have an asymptote is if that factor would cancel out. So if you had x squared minus 9, that's really x plus 3, x minus 3. The x minus 3's cancel out, so that actually would create just a hole at x equals 3. So if the factor in the denominator cancels out with the numerator, you'll get a hole. Otherwise, where the denominator is 0, that would be a vertical asymptote. So if you had like y equals 1 over x squared minus 4, that's really 1 over x plus 2 and x minus 2. So you would have vertical asymptotes at x equals 2 and x equals negative 2. So in general, where the denominator is equal to 0. And that's what we just talked about. After you cancel out common factors, because the common factors that cancel, that will have a hole. Anything that's still left over in the denominator, that's where you'll look for your vertical asymptotes. And as I said, slant asymptotes we'll talk about later. The rest is the more recent stuff we've been doing. So your increase-decrease test, do your first derivative, put it on your number line, find where the number line's positive and negative. So we've done that a lot. Use those critical numbers to determine where the local maxes and local mins are. We've done that as well a lot. Now remember, you could use the second derivative test if you wanted. Anywhere the first derivative is 0, plug those numbers, that same x value, into the second derivative. If it's positive, that means it's concave up and you have a minimum. If it's negative in the second derivative, that means it's concave down and you'd have a maximum. It's usually a little more tricky, a little bit trickier to do, so we really don't do it unless it's asked for. And then we can do our second derivative, and we can test for concavity. Remember, where the second derivative is positive, concave up, negative, concave down, and anywhere it switches, we would have our inflection points. So all that stuff is the more recent things we've been doing and probably are pretty fresh in your mind. Last thing we do is we just use all of that to make a sketch of the graph. Now when we're sketching it, you want to first draw in any asymptotes and points that we know. So the points that we know would be your intercepts, maxes and mins, and inflection points. Once you have those in your asymptotes, draw in with your concave up and concave down, and just like we've done before, then you'll use your increasing and decreasing to check to make sure it matches up. So here's a summary of them all together. We'll find our domain. We'll find our x-intercepts and y-intercepts. We'll check to see if there's even or odd symmetry. Now keep in mind, sometimes there might not be either. Again, the symmetry is really just something to make your life a little bit easier. It can be done without that. Look for your asymptotes, if you have any horizontal or vertical asymptotes. And then the more recent stuff, do your first derivative, do your increase-decrease test, check for maxes and mins. Do your second derivative, do your concavity, and find any inflection points, and then we'll sketch the graph. So the first example we'll look at is a rational function, 2x squared over x squared minus 1. And we're going to go through each of the guidelines and then use that to find the sketch of the graph. So first off, we've got our domain. There's nothing that will cancel out, no factors that will cancel out, because that's really an x plus 1 and x minus 1 in the denominator. So our domain is going to be all real numbers except for the things that will make the denominator 0. So we'll have all real numbers, but x cannot equal 1 or negative 1. Either of those in there will make it undefined. Next, we'll have our intercepts. For your y-intercept, remember, just put 0 in place of x. When you put 0 in place of x, you'll get 0 on top, so that just gives you back a 0 for the y-intercept. Now for x-intercepts, you want y to equal 0. So what will make this fraction equal 0? Well, a fraction is 0 when the numerator is 0. So that's 2x squared equals 0, or x squared equals 0. You'll get x equals plus or minus 0, which is really just 0. So this was our y-intercept. And if you've got the origin as a y-intercept, it makes sense. It should also be an x-intercept, because that is the point that is shared by both the x and y axis. Next, we want to see if there's any symmetry. When we put a negative x in, we'll have 2 times negative x squared over negative x squared minus 1. While negatives raised to evens will just come back positive. So this will really end up just being 2x squared over x squared minus 1, which is the same as our original. Because it's the same as the original, this has even symmetry, meaning it'll be symmetrical at the y-axis. Again, the symmetry, you're fine without it if you don't do it, but it can help you because we now know that if we can figure out half of it, the second half will just be reflected over the y-axis. So we found our domain, we found our intercepts, we found our symmetry. Next, we want to find any asymptotes. Well, let's find our horizontal asymptotes. Notice we have a degree of 2 in both the numerator and denominator. So same degree, you just look at the ratio of the leading coefficients, which is 2 over 1. So we'll have a horizontal asymptote of y equals 2. Your vertical asymptotes are what will make the denominator 0. So our vertical asymptotes will be x equals 1 and x equals negative 1. Next, we'll do our increase decreasing. So we've got to take the derivative. We have a quotient, so we've got to do quotient rule. We've got low d high minus high d low all over low low. If we neaten this up, we'll get 4x cubed minus 4x. Before the minus, we'll have a positive 4x cubed. So that will end up becoming a negative 4x cubed all over x squared minus 1 squared. And then when we neaten it up further, it'll just be negative 4x over x squared minus 1 squared. So we will use this to do our increase-decrease test. Remember, it does not exist at 1 and negative 1, so we need to make sure we put those on our number line. And we have to know when this will equal 0. Well, remember, a fraction is equal to 0 when the numerator is equal to 0. So negative 4x is equal to 0 when x is equal to 0. So we'll also put that on our number line. Keep in mind that you can't have maxes or mins at negative 1 and 1 because that does not exist, the graph there. So when we're plugging our numbers and our gaps into the derivative, it's important to note the denominator squared, so will always be positive, so it's not going to affect our sign. So all the negative ones, when we plug them in for x, you'll multiply it by negative 4 to get back positives. And the positive ones, when you plug it in for x and multiply it by negative 4, you get back negatives. So we are going to be increasing from negative infinity to negative 1, the union of that with negative 1 to 0. Okay, again, the reason we have to split it up is because at negative 1, we are neither increasing nor decreasing. And then we'll be decreasing from 0 to 1, and the union of that from 1 to infinity. Now, the only place we switch, and the only place we could have been, is at the 0. We went from increase to decrease, so that's going to be a max. So we'll have a max at 0 comma something. Now, normally we would have to plug that back into the original, but we already saw before that when x is 0, our intercepts there is also going to be 0. So that saved us a little bit of work. Next up, we've got to do the second derivative. We'll do that over here on the left. We've still got a quotient, so we'll have low x squared minus 1 squared, d high, which is negative 4, minus high, negative 4x, d low. For the derivative of the low, bring the 2 out front. We'll have x squared minus 1, raised to the first now, times the derivative of the inside, which is 2x. This is all over low, which is x squared minus 1 to the fourth now. Remember, when you're doing a second derivative of a rational function, pretty much every time there should be stuff you can cancel out. Remember, you can only cancel stuff out if it's part of every term. Terms are defined as the things that are all multiplied together. So those two things are separate terms. Notice in each of those terms and in the denominator, we have an x squared minus 1. So we can take one x squared minus 1 away from everything. On the top left there, we're now just distributing a negative 4 through. So we have negative 4x squared plus 4. On the right, if we start from the far right, you're doing a 2x times a 2, which is 4x, times a negative 4x, which is negative 16x squared, times the negative, which will be positive 16x squared. And we'll be all over x squared minus 1 cubed. And to finish neatening it up, we'll have 12x squared plus 4 all over x squared minus 1 cubed. When we go on our number line now, keep in mind 1 and negative 1 are still making the denominator 0, so those will need to go on. Now in our numerator, that's what will make the fraction 0. So we'll have 12x squared plus 4 equal to 0. That's 12x squared equals negative 4. When you divide by 12, you'll get negative 4 twelfths, which reduces to negative 1/3. And if you go to take the square root, you get x equals the plus and minus the square root of negative 1/3. Well, that's imaginary, so that will never happen. So negative 1 and 1 are the only things that we will need on our number line. Now keep in mind the numerator is always going to be positive, because when you square something it's positive and then you're adding a 4 on. So that's not going to affect our sign at all. When we put something like negative 10 in the denominator, we'll get 100 minus 1, which is 99, raised to the third as a positive. When you put 0 in, you'll get negative 1 to the third, which is a negative. And when you put positive 10 in, you'll get a positive back again. Even though we're changing from positive to negative and negative to positive in this number line, we do not get inflection points at negative 1 and 1 because the graph does not exist there. There are no actual points. So you always need to be careful. Just because it switches signs, if there's asymptotes there, or if there happen to be, say, a hole or something, you won't have inflection points there because there is no actual point. We can, though, list that it's going to be concave up from negative infinity to negative 1, and then again from 1 to infinity. And we will be concave down from negative 1 to 1. We've now completed our analysis. We'll next sketch the graph. First thing you should do when sketching the graph is draw in your asymptotes and any points that you found. So we had an asymptote at negative 1 and at positive 1 for the vertical ones. And our horizontal asymptote was at 2. Our x and y intercept were both 0, 0. So we can plot that. And we only had a max, which was also the 0, 0, and no inflection points. So now we'll keep in mind that that 0, 0 is a max, and we'll just draw in using our concave up and our concave down. Well, the first section on the left there needs to be concave up, and because it has to approach that y equals 2, it must be in the upper section. The only way you can be concave up and approach the asymptotes is looking like that. Next section we need to be concave down, and at that point there it needs to be a max, so it must look like this. And then we go back to concave up again, so it must look like that. And that is the sketch of our function. And there's just a nice version of the same thing that we just found, and notice it's very similar. We'll look at one more example. We've got f of x equal to x squared over square root of x plus 1. Let's start out with our domain. When you have a square root in the bottom, the things you cannot have is the x plus 1 cannot equal 0 because of the fraction, and the x plus 1 cannot be negative because of the radical. So the only thing left for x plus 1 to be is positive. Another way of saying that is x plus 1 has to be greater than 0. Well, when you solve for x, that tells us that our domain is just x greater than negative 1. Because it has to be greater than negative 1, we'll see eventually that we'll have an asymptote there. Now, along that asymptote at negative 1, the concave up and concave down, when we eventually get there, is what will tell us what direction we'll be going along that asymptote. Because we'll only be coming from the right side of that x equals negative 1, because we're not defined on the left side of it. Next, we'll do our intercepts. So remember, your y-intercept is just when you plug in 0 for x. We'll notice we just get back 0. We'll get 0 over 1. So that means also, that was our y-intercept. That also has to be an x-intercept. And notice 0 is the only thing that's making the numerator 0, so that's our only x-intercept. When you put in negative x, you get back x squared on top, so that checks out as like an even. But on the bottom, when you put in negative x, it stays as negative x. So it's not even, and if we were to negate it, we would just have a minus out front. So it's also not odd, so there's no symmetry in this case. And remember, again, the symmetry you can get away without doing if you'd like. It just helps you kind of shorten your workload if you do it. Now our asymptotes. You can think of the bottom as being like an x to the 1/2. Well, you have an x to the 2 on top. That's greater than 1 above it, so there's no horizontals. And we mentioned our vertical would just be at negative 1, because that's what's making the denominator 0. So we just have a vertical asymptote at x equals negative 1. We next have to do our first derivative. So we have a quotient rule. So we'll have f prime of x equals low. So that's square root of x plus 1 times d high, which is 2x, minus high d low. Now, the derivative of the bottom, think of it as being raised to the 1/2. So you'll have 1/2 x plus 1 to the minus 1/2 times 1, because that's the derivative of the inside. All over low, low. Well, when you square a square root, you just get what is there. There on the inside, an x plus 1. Now, this is going to be a little bit messy to simplify. We'll get 2x square root of x plus 1. The x plus 1 to the negative 1/2 will move to a denominator. We can't just move it to the denominator all on its own because everything did not have that term. So we'll have a negative x squared over 2 square root of x plus 1. The 2 is coming from the 1/2, and the x plus 1 to the negative 1/2 is the other square root there in the bottom. And this is all over x plus 1. So to clear the denominator, we can multiply on top here by 2 square root of x plus 1, and also multiply on bottom by 2 square root of x plus 1. This 2 square root of x plus 1 will have to distribute to both parts. The 2 will multiply with the 2x to give you 4x, and then square root of x plus 1 times square root of x plus 1 will just give you x plus 1. In the second term there, the 2 square root of x plus 1 will cancel with the 2 square root of x plus 1 on the bottom, and you'll just have minus x squared. And on the bottom, we'll have x plus 1 times the 2 square root of x plus 1. To neaten this up a little, distributing the 4x will give us 4x squared plus 4x minus x squared. Think of that square root of x plus 1 as x to the 1/2, or x plus 1 to the 1/2. So you have an x plus 1 that's to the first, and an x plus 1 that's to the 1/2. So that means you'll have an x plus 1 now to the 3/2. Your exponents, and we'll have the 2 out front. One last step to simplify it. We can bring those x squareds together, and we'll have 3x squared plus 4x all over 2 times x plus 1 to the 3/2. So this one's a little bit messier than the last one. We want to know, when will this be equal to 0? Well, on our number line first, let's think about when is it not going to be defined. Well, that'll be the case when x is equal to -1 or 1. Or sorry, just -1. 1 would be okay because it'd make it a positive 2 in the parentheses. We know to the left of -1 it doesn't exist, so we don't have to worry about that. And then we need to see when will the numerator be 0, because a fraction is 0 when the numerator is 0. This will be x times 3x plus 4. We'll get x equals 0. And this will be 3x equals -4 when we subtract it over, x equals -4/3. Now, even though we get -4/3, that's going to be in our does not exist section. So that's not going to go on our number line. We'll just have the 0 on the number line. So there's only 2 spots that we need to check. In between the -1 and the 0, and then above the 0. Well, let's say we had something like -1/2. When you put it in the bottom, you'll get a positive. In the numerator, the -1/2 will make this part here a -2. -1/2 squared will be a 1/4 times 3, so you'll get 3/4. 3/4 minus 2 will be a negative, meaning this section's negative. When you put positives in, there's no minuses anywhere, so everything will just be positive. This means that we are increasing from 0 to infinity, and we are decreasing from -1 to 0. When you go from a decrease to an increase, where there's a point, we'll have a min. So our min is going to be at 0, something. Well, we already determined that that was an intercept, and it was just 0, 0. So we'll have to take our second derivative now, which will be a little bit messy, and we're going to go from right here. So we'll have low d high. So we'll have 2 times x plus 1 to the 3/2 times 6x plus 4. Then we'll have minus high d low, so 3x squared plus 4x. D low, the 3/2 will multiply with the 2 out front, giving us just 3. And then we'll have x plus 1 to the 1/2 times 1, because that's the derivative of the inside. And that's all over low, low. Well, the 2 times 2 will give you a 4. Something to the 3/2 times something to the 3/2. Well, basically the square roots will cancel out, and you'll be to the third. So I have x plus 1 to the third. Now remember, when you have a rational function, the second derivative almost always something cancels. Everything has an x plus 1 to the 1/2. So this will be gone. This will now be the 5/2, because 5/2 is 2.5, and this will now be a 1. We can distribute the 2 through, and we'll get 2x plus 2 times 6x plus 4 minus that far right parenthesis is now just a 3 times a 1, so I'm going to stick that 3 and distribute it through, or actually we'll just write it as a 3 for right now. 3 times 3x squared plus 4x all over 4 times x plus 1 to the 5 halves. And to neaten this up, we've got to FOIL the left-hand thing in the numerator. So we'll get 12x squared. We'll get plus 8x plus 12x plus 8. We'll distribute the negative 3 to get negative 9x squared minus 12x all over 4 times x plus 1 to the 5 halves. And we'll neaten everything up to give us 3x squared plus 8x plus 8 all over 4 times x plus 1 to the 5 halves. And we want to know, when is that going to equal 0 for our number line? Well, on our number line, we've got to put negative 1 down, because that makes the denominator 0. We know to the left of it, it does not exist. We have a quadratic. Doesn't look like it will factor too nice. If we do our discriminant, our b squared minus 4ac, the part under the radical of the quadratic formula, we would get 64 minus 4 times 3 times 8. That'd be 64 minus 96, giving us negative 32. So the numerator has imaginary roots, meaning there'd have be no real roots, meaning it's never going to be 0, so we won't get anything else on our number line. So if we pick something in this gap here to the right, 0 would be the easiest thing. You'll get back 8 on top. You'll get back 4 times 1 on bottom, which is positive. So it's always positive. So that means from negative 1 all the way to infinity, it is concave up. It's never concave down, so you can't have any inflection points at all. So our first and second derivatives there were a little bit challenging, but something that is manageable if you work through it. So we'll now sketch the graph. The things that we know we have a vertical asymptote at negative 1, and that there will be no graph to the left of it. And we have a intercept, which is also a min at 0, 0. Next, we'll just draw in our concavity. We know it's always concave up, so that means it should look something kind of like this. And it doesn't approach anything else, so that is our graph. Let's just check and make sure our increase and decrease makes sense. We should be decreasing from negative 1 to 0, which we are, and then increasing from 0 to infinity, which that checks out as well. A nice version of the graph looks kind of like that, if you were to see it on the calculator. So you go through these steps to find your sketch. When you're sketching, you draw your asymptotes and any points that you know first, then draw in with your concavity and check with your increasing and decreasing. That's all for today's video. We'll see you next class period.